Okay, so we are very happy to welcome Jernej from ICTP Trieste in the University of Maribor. And the title is From Lebesgue Measure Preserving Maps to Surface Homomorphism with Pseudo-arcs and pseudo-circle attractors.
Thank you very much. I'll just check if... Okay, so would this need to work?
If not, let me show you just
So it is inside the USB.
So we just need to put the mouse here. Let's try now.
Okay, perfect.
Okay.
Yes.
You just start recording. Sorry. Okay.
Okay. Thank you very much for the invitation. Finally, we found a spot for me to visit. And today I will speak about the topic that is very fond to me. It's between the one-dimensional Lebesgue measure preserving usually non-invertible maps on the in one dimension, so on one-dimensional connected manifolds, so interval or circle. And I'll also discuss a bit how to get to more complicated objects, which are pseudo-arc and pseudo-circles, and even make them somehow attractors of some planar or two-sphere homeomorphisms. And my talk is going to be based on these four papers. So yes, this is joint work with Piotr Oprocha, Jozef Bobok, and Serge Troubetzkoy. Piotr is listed as the first author because the next slide, all of the papers that are listed here that I will speak about, he is one of the co-authors. And yes, so actually today I will speak mainly in the most detail about the newest of the papers, which is with Jozef, Serge, and Piotr as the co-authors. And this is about the generic Lebesgue measure preserving maps on interval having topological, having metric entropy 0. But I will also mention the results from all the other 3 papers. Okay, and if we get to the story, first I will introduce some basic concepts and then motivate how we came to this study before going into more details. So we say that continuum is a compact connected metric space. And I define inverse limit space as the collection of all possible backward orbits if you apply some pre-chosen map F on this space. And we equip this set with the product topology, which punishes more if we take 2 points. They are further apart if they differ on the first coordinates. If they differ on the late coordinates far away, then they are close together. And the natural extension or the shift homomorphism is defined by taking a point and applying just F to all of the coordinates. So this is a point in X hat. We apply F to all of the coordinates, and what happens is F of X1 is X0, F of X2 is X1, and so on. and on the zeroth coordinate we have f of x 0. So it's the opposite of the forgetful shift. I could also define it as a forgetful shift, it doesn't matter. It's the shift that gives birth to another coordinate. And for instance, the prototypical family, if you just look at this inverse limit spaces, and let me just mention that I will speak about the inverse limit space as a technique that we use, not that I would study the inverse limit spaces on their own. It's a technique that we use in the process of our studies. But if you want to look at an interesting family of inverse limit spaces, the prototypical family is taking the symmetric tent map family and its inverse limit spaces. And if you draw the inverse limit spaces, they look something like that. They are one-dimensional. They are one-dimensional continuum. That's enough to say at this point. And why is this? Why is using inverse limit technique, let's say, useful? One of the main things is that we know that maps F and the shift homomorphism share many dynamical properties. They are translated from from this setting to this setting. So, for instance, such properties are periodic points, topological entropy, the mixing properties, both topological and matter theoretic. So, in some sense, if you want to create a more, let's say, complicated system, you start with a system that you understand. And you say, this is on the interval, you understand the system well, and then you lift the dynamics on the more complicated space. And then this is useful for many constructions. First I will speak a little bit about the motivation, and then I will come to the more technical part, okay? And then, if I ask you how to think about the inverse limit spaces, it's not so, I mean, I just give you the definition, but how do you think about it? And a good way for a dynamicist to think about it is through through this approach. So I define a natural projection, specifically the zero projection, by taking a point x and looking at its zero coordinate. And this pi 0 semi-conjugates my shift homomorphism f to the map f. But now, if I want to have an invertible dynamical system that semi-conjugates to this f, it will need to factor through the pi 0. Because the pi 0 projection it will decompose this complicated space in the parts that will be injected by f. So sort of it's the minimal, the inverse limit is the minimal invertible system which extends f. So that's a good way to think about it. Yeah, that's the bottom line. If we want to have a system that is more complicated but semi-conjugates to f, we will need to go through this pi 0. Okay, and
started from interval, of course, can be anything.
it can be anything, yes.
Usually, historically, people started with units with a circle.
Yes, and got solenoids.
And then solenoid.
Yes. Yeah.
It's more complicated because it has one singular.
That's true. Yes. If maybe for the sake of the presentation, I should mention the solenoids, but yeah, the solenoids don't embed in R2, and I want things to be embeddable in R2. That's my because so we will get to the part where it's going to be the surface dynamics, and yes, I want to think about the plane.
You is some one-dimensional branch.
Exactly. Yes, but
In Warsaw, the first man who studied such model map, but full
yes,
parabola and inverse was
Mhm.
Jernej.
yes, yes.
He had PhD student Piotr Oprocha.
Mm-hmm.
He didn't finish PhD.
But
He started.
I think they wrote some papers, or he wrote some
He
papers.
wrote something.
Yes.
He started.
Mm-hmm.
Switch it to other.
Right.
He is still at the university. Or maybe not, but he is around.
Okay. Okay. Yes. And okay, let me get to the point of this story that I'm trying to make. Actually, my PhD was on studying the inverse limit spaces of pentams, of the symmetric pentam family, but in perspective to apply it to make these attractors as of some planar homomorphisms. And there is a technique, a general technique that does this for actually, okay, in this talk I will focus on just let's say interval and circle maps. So for interval, for any interval map, you can lift this dynamics and create an attractor of a planar orientation preserving homomorphism. And yes, when I was studying the exactly 10 inverse limit spaces from this aspect for my PhD, I was in the second year, or the third year of my studies, and a paper appeared by Boyland and Carvalho and Hall, which did exactly that, exactly what I was doing for, let's say, a big chunk of my PhD program. They gave a complete description of boundary dynamics. So what is happening on the boundary, you put this one-dimensional object in the plane, and you look what is happening just on the boundary of this one-dimensional space. And they actually characterized the boundary dynamics of this of a parameterized family of orientation preserving homomorphisms of the plane, which attract with attractors exactly homomorphic to these guys. And then, yeah, a couple of years later, our result appeared, which was actually the showing the analogs of what they had. So this was a sort of a very nice, very big paper also. However, we used a completely different techniques. They used topological techniques, and what we used was symbolic dynamics. We coded every point in this inverse limit space with some sequences of symbols, and we studied these attractors using these symbolic techniques. But they
What do you
use
mean by boundary? Parameter boundary or space it is lower dense?
Boundary meaning if you put a one-dimensional, let's say, continuum in the plane, you look which points you can pull from the outside. And this is Karatadori's prime end theory.
Okay.
It's called Karatadori's prime end theory, which formalizes this approach. So
Would you be interested, as you said, in the extensions to plane homomorphism? So that would seem
yes, yes,
classify and
yes.
So I don't understand why would you only be interested in the boundary dynamics? You see, it's like, isn't it more natural to really understand how they extend?
But this is with the given technique. The technique is known, how to make it a orientation preserving homomorphism of a plane. That's known. So it's this one particular technique that if I have time, I will mention at the end of my talk. And then with this technique, it was already interesting to study what's happening on the boundary. You are completely right. One related question is, well, how many homomorphisms of these guys exist so that the so that we can extend them to the whole plane? That's a different question, and a very good question, actually. And we have some results in this direction as well, but I'm not going to speak about it. Now, this, yes, it's about one specific. Yes,
so you also have the choice of embedding.
Of course.
Okay. So
of course.
Study for everything.
So this is given a fixed choice of the embedding. But even for this, it's very hard. I mean, there were no studies in the past. Studies of parameterized families of homomorphisms and the relation to boundary dynamics. So there was no such study.
So there is a canonical one that is used.
Yes, exactly. Yeah. There is a canonical one. Right. Okay. And so one interesting thing here is what they discovered is that that this boundary dynamics is very rich. So from the Caratadori's prime-end theory, you can define prime-end rotation number for every homomorphism, and they showed that the prime-end rotation number of this family varies continuously in an interval. I think it was from 0 to 1/2. But this function was like a devil staircase function. But the point being that what's happening on the boundary is very rich. And one interesting thing here is it's connected to the result of Sonja Stimatz and also our result with Henk and Anna. Actually, for any two parameters, if the critical point has either finite orbit or is non-recurrent, then the two inverse limit spaces are not homomorphic. And this is restricting to okay. I'm a little bit cheating here. Here I should say the core of this map. So actually, this is the inverse limit restricted to the dynamical core. And so I made a typo here. It should be a core because Sonja Stimatz, Henk Bruin, and Maribor, they proved the Ingram conjecture, which says that for any two parameters in this parameter space, without this assumption, the inverse limit spaces are not homomorphic. That is known as the Ingram.
On which have different entropies?
Yes, they have different entropies, but you know that doesn't classify them. It's the other direction of what you need, right? You can have two conjugate maps, but it's the inverse limits are not homomorphic. Right. So the point here being that these inverse limit spaces that were studied here, they are non-homomorphic. However, and maybe one could say, okay, maybe that's why this boundary dynamics is also rich. However, this motivated us with Piotr to, well, we also had other motivations, but this was one of the motivations. It motivated us to construct a parameterized family using this same technique, this technique that we mentioned, the particular kind of embedding, they're very continuous with the parameter that always the pseudo-arc is the attractor. We have always the same attractor topologically. However, we have actually the same boundary dynamics happening as in the previous case. So we showed that it doesn't matter if you have different, so that different spaces is not the reason for different boundary dynamics.
What is your parameter?
The parameter is it's on the interval, 0 to 1.
But it is just slope of symmetry.
It's a little,
topological
it's a little bit more complicated. These maps have these maps have infinite topological entropy, all of them. You know. So it's not determined by the topological entropy. It's a little bit more intricate.
So one should ask about the mean dimension, maybe. Is it not?
Actually, we are working on this now.
No, but my question is that you just can't.
Yes.
That's.
That was the previous slide.
Yeah, and now you discuss
Yes.
more general.
Now this is more general.
That's why parameter.
Yes. Is
It's
it
different
going to
parameters with the same.
be, exactly, it's going to be chosen differently, yes.
Always on the interval.
Sorry?
Always on the interval.
Yeah, this will be on the interval.
Okay.
The technique will be this technique again the same, but here interval.
Finite number
here.
of monotonicity.
No. If you
Infinite.
have pseudo-arc, then you cannot have finite monotonicity.
Yeah.
So these maps are actually very complicated, here and here. They are very complicated, and that's the next step, what I want to talk about. So I want to talk about the pseudo-arc, and some of you know about it, know a lot about it. So the pseudo-arc was defined by Knaster as the first example of a non-degenerate hereditarily indecomposable continuum. Now, what do I mean by hereditarily indecomposable? Continuum is decomposable if there exists two subcontinua, so that the union is the whole continuum, and it's indecomposable if it's not decomposable. Hereditarily means that every subcontinuum is indecomposable. So this is a space, so that every of its subcontinua is indecomposable. And it was an open question at that point, and Knaster answered that there exists such a continuum. Then Moïse in 1948 constructed seemingly a new example, which has all these subcontinua homeomorphic to the big continuum. Which other continuum do you know that has this property? So continuum being compact connected metric space. The interval, right. Every subcontinuum of the interval is like an interval. So the interval is another such example. And people were asking at that point, does there exist another continuum different than the arc with this property? And Moïse proved that there is one. And that's why they call it pseudo-arc, because it has this intricate property, the same as the arc. And actually, just one remark, in the plane, there are only two such continuum, and these two are the only. So, arc and, non-degenerate, of course. Arc and pseudo-arc. And then, Bing, in 1948, constructed another example because there was another question about homogeneity. If there exists a homogeneous continuum that is different, that is in the plane and is different than this circle. Yeah, exactly, non-degenerate and different from the circle. And pseudo-arc is again such a continuum. And then Bing in 1958 showed that all these three examples are actually homomorphic to one another. Yes, and okay, if I did a remark here, it's proper to do a remark here. not so long ago, maybe 10 years ago, maybe 8 years ago, Logan Hain and Lex Overstegen, who actually proved that result that I mentioned here, also proved the result that there are only 4 homogeneous continua in the plane. So, and these 4 are point, pseudo-arc, circle, and actually at some point it was proven already that if you have a continuum in the plane that is homogeneous, then a circle of this continuum is also homogeneous. So it's actually a space called circle of pseudo-arcs. I won't define it here. Yes. And now I wanted to discuss what characterizes crookedness in the interval. So as it was nicely observed, we will work on the interval. And what I want to do now is explain to you a property that characterizes the inverse limit being pseudo-arc with this map. And what does this say? So it's mouthful. It's good to look at it maybe on this example. It says that a map is delta crooked, and let's think about, first think about 1/3 crooked. What would 1/3 crooked be? I want a map, and I want to restrict a little bit even more. I want to come from this endpoint, from point 0, 0, to point 1, 1, with the graph of the map. And my question is how to do it in a crooked fashion, in 1/3 crooked fashion. I divide this box into 3 boxes. The first box being this horizontal line 1/3 and everything that's below it. The second box being here, and the third being here. And why is this map F 1/3 crooked? Well, first thing is, what does this definition say? Between this point, okay, maybe first question. Is it possible that we cross these 2 boxes and end up here without turning back? The answer is no, because then we couldn't find 2 points. So if I redraw this here, 1/3 here, 2/3 here. If I would do this, I wouldn't be able to find, okay, let me show you this. So for me this is now C, A, and this is D, and here is B. And can I find 2 points, C prime, D prime, C prime being smaller than D prime, so that the distance between B and F of C prime, between B, this value, and F of C prime is smaller than delta, smaller or equal than delta, and between A and D prime is also smaller or equal than delta. I cannot, right? This would require me to do a pattern like this, right? After I'm delta close to this point, I need to be delta close to A. So this condition implies zigzag pattern. So we cannot cross the 2 boxes with a straight line. We realized. So, but this map is sort of the simplest possible 1/3 crooked map that we can get. Because if we look at okay, we didn't cross the two boxes, everything okay. But also, if we check how to get from, if A is 0 and B is 1, we can find C prime and D prime being exactly as on this picture. And the value of C prime is delta. The value of C prime up to 1 is exactly delta, the difference, right? And the difference of the values between 0 and D prime is again delta. So we found it. Right. And to understand this, I wanted to give, okay, it's good to understand this definition properly, so let us do another example together. Now, I want 1/4 crooked map. And again, I want to start from here and end up there with my graph. As there, let me divide this in 4 boxes. Okay, and now we will go together. I can cross 2 boxes. That's okay. I cannot cross 3, because then locally I'm not delta crooked anymore, 1/4 crooked anymore. So I can start like this. I cannot cross 2 boxes anymore, so there is nothing else to go down. And to get to this box, to the 3/4, I do it in this crooked pattern. Everything okay, right? I didn't cross 2 boxes. But now, okay, now tell me what I can do. I want to get up to this point in this crooked fashion. The natural thing, what one would think of, would be, okay, do this. Is this okay?
No, you get a problem with 0 and 1.
Exactly. You get a problem between 0 and 1, right? Because, what did we say? For these 2 values, if I want to be crooked in between them, I first need to approach delta close this value, and then delta close to this value. But I didn't do that. So I cannot draw a straight line here. I need to go down, at least up to here, because now I know that I'm delta away, I'm 1/4 away, and then I can go up. But again, I cannot cross 2 lines, so I need to go down and now up. So you can see that you have this recursive pattern inside. It's the local crookedness condition is you cannot cross 2 boxes. The global crookedness condition is, okay, you actually need to do everything what you did before, and then do a repetitive thing to go up and not cross 2 boxes. So now we understand what this crookedness condition says. And there is a theorem, which is actually by means and transfer, but they rephrased Dink's theorem from 50s, because he did it on the inverse limits. Non-degenerate continuum is a pseudo-arc if and only if this map F is a bonding map, is such that for every delta there exists an iterate n, so that the f on the power n is delta crooked. So we cannot have these maps, right? Because these are only 1/4 crooked for f. We don't know what's happening. What if I would give you 1/5?
So when you say delta crooked, you mean for every A and B, for every choice?
Yes,
Okay.
yes, yes.
It's written there, sorry.
Yes. Okay, yes. So this, of course, needs to hold for every k. Yes. Right. So this condition is that we need to look at the iterates, and these iterates need to be more and more crooked. Okay? So in particular, this guy is probably not good. And actually, it's not so hard to prove that a map that is going that is delta crooked for any delta. I mean, you know, this condition that you can find an n so that such that f on n is delta crooked. Such map cannot be piecewise monotone. And actually, okay, I want to mention here the first example of such a map that its iterates are crooked, delta crooked for pre-given and pre-given delta. The first such map was constructed in the 60s by Henderson, and it had zero topological entropy. So it's a pretty simple interval map, which has, so he starts with on the 0, 1 with x squared function, and then he introduces some teeth inside in a very specific places. And then he was able to show that the inverse limit is actually a pseudo-arc. So this example is, up to now, the simplest example that we know, and it gives the pseudo-arc in the inverse limit. And okay, yeah, that's just, first, I've proven that there are uncountably many non-conjugate maps with entropy 0, so that the inverse limit is the pseudo-arc.
Isn't everything attracted?
Exactly. Everything. So everything is attracted to 0. But you could have you could have a term with you could conjugate with 1 minus x, and it would be to 1. Yeah. Right. Everything is attracted to 0. But if you are thinking about inverse limit, then you're looking at pre-images. So yes, it's pre-image attracted to 1. Yes. And yeah. So there are actually many, uncountably many non-conjugate maps like this that give pseudo-arc, but they have topological entropy 0. Okay, I won't go into details about this today. And here, for instance, for a long time there was a question if there exists a transitive map on the interval that that the inverse limit is a pseudo-arc, and this was only constructed in the 90s by Piotr Oprocha and Will Transu. They gave a description of such a map. So this is sort of a non-trivial problem to obtain the maps so that the inverse limit is the pseudo-arc. And there is a computer simulation of an approximation of the pseudo-arc, which can also be obtained as taking the nested intersection of these chains, one in the other, and they all need to have a crooked pattern. So it's something similar to what we described here. Yes.
When I look at this picture, you know, on the right-hand side, it seems even it's disconnected, right? There is this more white. You see in the corners to the right. So that's really. So all these white spaces, is that because? I mean, is this because the quality of approximation? I don't understand how to read this picture exactly.
Yes,
you know what I mean?
You are right. I mean, okay, it does connect here. It connects here. However, there was a paper by Means and Lewis which said you cannot draw the pseudo-arc, which is actually telling that if you use a raster, if you use pixels, and you want to draw the pseudo-arc, in the end, what you will get is either a blank picture or a black picture. So
it's not computable?
No, the resolution doesn't give the outcome. Right? because you always have some kind of resolution, but given any non-infinite resolution, you will get no picture. Well, you will get either blank or black. And then Piotr was always upset when we said, okay, you have pseudo-arc here. And he said, how can you draw pseudo-arc? You cannot draw it. Just leave it black or draw everything. So this is Piotr Meets. He unfortunately passed away this year. Right. So,
He was worked so many years
Yes.
ago.
yes. He was in Auburn. Right. Okay. So, and pseudo-circle is actually another such space, which is, okay, it's connected to pseudo-arc, but the difference is that, well, there are many differences, but it's a circle-like continuum. The previous one was on the, it was changeable continuum. We could get it as inverse limits on the interval, but this one is sort of, it has a circle shape. So it's closer to solenoids as the pseudo-arc. And it was defined by Ding as a unique planar, hereditary proposable circle-like continuum, which separates the plane into two parts. And by circle-like, I mean inverse limit on the circles. But
this picture, I think, is more convinced better,
yes,
no? than
the Jan's picture. Yeah. So it depends. He took some map on the, he was looking at, let's say, things in the annulus. That's why it turned out to be this shape. But yes, this one is more convincing. Okay, and this one is the one that is more convincing, right? Right. Yes, but the connection is every subcontinuum of the pseudo-circle is actually pseudo-arc. Every proper subcontinuum, non-degenerate, right? And not the full thing.
So it separates in exactly two parts?
Yes, it separates the plane in exactly two parts. It's a Hoffman theory. Right. And I won't tell everything here. Maybe I'll just mention, what I wanted to mention here is that both pseudo-arc and pseudo-circle appeared already in the literature. However, pseudo-circle is the one who, appeared in the dynamical systems literature. The pseudo-circle was the one who appeared much more. And this was started from 82, when Handel constructed pseudo-circle as a minimal set of a C-infinity area-preserving planar diffeomorphism. And if you remove area-preserving, it was actually a planar attractor. So points, all the points in some domain got attracted to this pseudo-circle. And one thing that we struggle with as this small community working on these questions is to provide examples that would actually be smooth, very smooth, like this C-infinity area preserved, C-infinity planar diffeomorphisms, and having a family of attractors. So we struggle with putting these two together. This inverse limit approach probably doesn't get it. But yeah, I just wanted to emphasize this result. And this was a big deal. And it's still a very nice, it's a very nice result to look at. And yeah. And actually, it would be very nice to have a parameterized family of such, let's say, attractors with the C-infinity planar diffeomorphisms. And actually, we are working with Piotr and his PhD student on variation of this question. Right. Okay. And now we came to the second part of the story, which are and this is now one dimension. And this is about the back measure preserving maps. By lambda, I will denote the back measure on unit circle, and unit interval. And the two main spaces are going to be the spaces of maps that preserve Lebesgue measure. And we know this set with the metric of uniform convergence. We will only look at the metric of uniform convergence, this Freer metric. And in this case, it's not difficult to observe that these spaces are complete metric spaces. And I will speak in what follows. I will speak about generic properties quite a lot, and a property. Okay, a property itself is called typical. The set of all maps with this property is a residual, so contains dense G delta set. And maps that have this property I will call generic. Okay, that's usual. So I will think about genericity in topological terms. Okay? And the basic example here is the tent map, full tent map. Take an interval A here, look at its measure, look at its pre-images, look at the measure of the pre-images, sum these two up, and the measure is exactly what's the measure of the set A that you took. And actually, there is a very useful observation. It's a very simple but very useful observation that says that map F is Lebesgue measure preserving if and only for any non-degenerate part if you sum the measure of all the components over the measure of the full interval that you took is 1. So it's the phenomenon that I described on this full tent map, but in more generality, it speaks about components. You don't need to have piecewise linear, right? But again, the sum of these reciprocals needs to be 1, and then your map is Lebesgue measure preserving. So it's good to think about maps, Lebesgue measure preserving maps in these terms. Okay. And one other thing that this full tent map, this full tent map has is the property that the closure of the set of periodic points is the whole space. Closure of the set of all periodic points is actually the interval. And I will denote these spaces with CTP. And okay, yeah, dense periodicity is usually, in most of the definition of chaoticity, it's the prerequisite. But why did I mention this? I mentioned it because there is a nice remark which says that the following three conditions are actually equivalent. Having a map that preserves a Lebesgue measure is equivalent to having a map that preserves a non-atomic probability measure with full support. Actually, okay, this is not difficult to see because you just use the push forward. You just push the measure to whichever desired measure with full support you want, right? So the equivalence between 1 and 2 is not surprising at all. But it's also equivalent to having a map with dense set of periodic points.
So this is specifically for segments, when I is a segment?
Exactly, yeah. In higher dimensions, this isn't. Something similar holds for the circle, but yeah, I stated this one first. Right, so we have the equivalency of these three.
It seems that we would put smaller and smaller masses on the periodic points, no? When we take some weak limit, maybe?
Yes. Right. Okay, so yeah, one direction from 1 to 3, this is a Poincaré recurrence theorem. Right? Poincaré recurrence theorem says that if map preserves a non-atomic probability measure with full support, you will get, with any point, you will get back to the initial state at some point. So the set of recurrent points is dense. However, there is a result by Bloch and Coven from 80s who said that for interval maps, the closure of recurrent points is the same to the closure of periodic points, and therefore, in our case, the whole interval.
Close the column.
Yes. Yes. But the other direction is not so obvious, maybe. Actually, if you want to go from a map, this map has a dense set of periodic points. How do I know that F preserves a non-atomic probability measure, some non-atomic probability measure with full support? Actually, there is a paper of Barge and Martin which says that, so this is from Barge and Martin, from 90s. They say that if F is in CDP, then there exists a sequence of intervals, possibly countably infinite sequence of intervals, JI's intervals, closed intervals, so that F square restricted to JI is topologically mixing for every I. And if we take I minus union of JI's, every point here has the property that the second iterate is identity. So maps with dense periodicity, the second iterate of the maps with dense periodicity, because, okay, second iterate because you can reverse, you have reversing of the endpoints, right? This is the peculiarity why the second iterate. But along the diagonal for the second iterate, you have boxes, possibly countably infinitely many of them, where your map is topologically mixing, but in between you have identity. And this was a very nice, actually a very nice paper, which tells you a lot about the, of course, tells you a lot about the structure of maps with dense periodicity. But having this, that we can decompose the...
Sorry, but for generic map, you will not have this identity part, you just do report.
Yeah, exactly, yeah. So for, you have, here, Ji would be just, this would be the whole interval I. You would just have one.
Okay.
Yeah, exactly. But, you know, yeah, we are interested in others that are. Right. So, we are topologically mixing here. And Sasha Bloch, also in the 80s, proved that mixing implies specification. So we can look at the restrictions of these maps here. Mixing implies specification, but specification is resolved by Sigmund from 60s, implies that we have a non-atomic, that we have that F restricted to this part preserves a non-atomic probability measure with full support.
of doing. So this other more, let's say, elementary argument, you cannot make it work. I mean, I understand that there will be a problem if you put masses on this periodic. You need to check that you don't have mass escape from some small interval.
Yeah.
But that doesn't seem so hard to me. No. I don't know, because maybe you can, for example, you can ask yourself, is it true that this probability measure with full support is, or you can look at the, let's say, the weak limits of atomic measures supported on periodic points.
Yes.
You can ask yourself, what would you see there?
At some point I was thinking in this direction, but there was some problem with this
It
argument.
will not be invariant, right? If you just take periodic point, because each is a point that has extra images.
Right. Yeah. So it's possibly not invariant.
I'm always
Oh, if you put zeros everywhere else? I see.
Yeah.
Yes,
Is the limit agotic?
Sorry.
Is the limit, this measure you discussed, agotic?
Yes. No. Okay. The measure here that I'm discussing.
There is no limit.
There's no limit. No.
But if you just do some periodical bits, then the limit is also no limit. Not specification.
Yeah. You can discuss about it, but at some point I think I was thinking in that direction, but there was some problem with the
so
argument.
it's not so easy. Okay.
So-
because this seems like a more, let's say, advanced argument, right?
Yes, the layers of
Layers
3
of-
papers, right? Maybe
Right.
this shouldn't be that difficult. But yeah. So we can discuss about this a bit more. But okay, also for this circle, you have a similar thing. If you remove irrational rotations, right? Irrational rotations are problematic. They have no periodic points, but they preserve the back measure. However, as soon as you remove them, the world is nice. You still have the equivalence there. Right. Okay, and I want to get to this, the next slide, and that will, I think, we will finish with that slide because, yeah. Actually, what we've proven with respect to the previous, with respect to delta photons that I was explaining to you, what we've proven is that this set of maps, so that the map F gives the pseudo-arc, that's actually just rephrasing it, the map F gives the pseudo-arc in the inverse limit, is a residual subset of C lambda. So this property on the values, very strong property on the values, is actually not restricted in the back measure preserving setting. It's actually, you find it everywhere. It's a generic property. And yeah, so I was thinking about this already in my PhD program, but at that point I didn't have tools to prove it yet. But when I met Piotr and we started discussing, we found a way how to prove it. And actually, a similar statement holds also for the back measure preserving maps on the circle. Having the degree 1 maps gives pseudo-circle being the generic inverse limit. Both of that we can prove for the back measure preserving and also for then set of periodic points, having some conjugacy argument, how to get to the CV. So, and this is very different if we remove the back measure preserving, or if you want dense periodicity, if we remove this condition and just look at the maps on the interval, it was proven that such maps that give the pseudo-arc are nowhere dense, actually. It's a very tiny set, nowhere dense set of maps that gives the pseudo-arc. However, when you get to this interesting case that we have here, the, let's say, CVP or preserving some measure, then it's all of a sudden generic. Right. And I will stop on this slide a little bit longer. I will, but I will do the board presentation from this point onwards. That's why I said I would stop here. So up to now I was giving the more relaxed version of argument, but here I will do it on the board. So there is an observation that the set of maps with topological entropy infinity form a dense G delta set in C lambda. And actually, how to see this? This is not so difficult to see. Actually, if we have identity or 1 minus identity, these are, let's say, problematic parts. But as soon as we don't have these two cases, we know that our map will have a transverse fixed point. And around this transverse fixed point, we can perform some particular kind of perturbations. We call them window perturbations. We take a window, and in that window, we make copies. We attach together copies of this. We shrink it to a smaller interval, this image, the graph, and then we take the copies. And we can do this finitely many times, however large we want. And we can reduce this box around the transverse fixed point also as much as we want. So this can be very, very tiny. This perturbation is small. And we can have huge amount of hooks, a huge amount of horseshoes around this fixed point. So this shows that and if we have a horseshoe there, the topological entropy will increase. It will be log n for n arbitrarily large. So we will have we will have entropy infinity arbitrarily close to any given map. So this gives the denseness. However, also, because we have a transverse fixed point, we know that these perturbations are stable. So around any of these perturbations, we can form an open set, and that, because we are in the superior metric, and in that open set, all of the maps will also have that many horseshoes. And this we can do for any n arbitrarily large, which means that it's also an open condition, which gives the generic. So it's just an observation. Right. And now my question to you is, can you guess what's the metric entropy for generic? For lambda.
Because you can produce series of the lambdas.
By metric entropy, you mean the measure?
Measure. Okay, yeah. Measure theoretic entropy.
I hate that terminology.
Metric. I also don't like, but we...
Measure theoretic entropy, of course.
What?
In the 7th,
but I think it's out of favor, no? I think it's less used.
It's less used, yes.
But it's true if you go back to the classics all the time.
Yeah. But measure theoretic entropy. Do you have a guess what would be the measure theoretic entropy? And we were struggling with this question for quite some time. Infinity, right?
Yeah, we were the same.
Yeah, you have the...
you need to start with finite partition. But then you go to the limit with final
Yes.
You ask what is generic.
What is generic value of measured theoretic entropy? Yeah. And we were struggling exactly with this question: how to what partitions should we take and how to prove it. We didn't have the first step, first approach to solving the problem, and we were struggling with this for quite some time. And even Jozef Bobok and Serge Troubetzkoy, they had this question posted in one of their papers, which was published, I don't know, 5 years ago. And we were constantly thinking a little bit about this question, and it wasn't clear to us how to approach. But then we saw a paper of, actually, Mark Polycott showed a paper of Perry to Serge Troubetzkoy, and actually using his techniques, we could prove that for the full tent maps, we have metric entropy 0. And I mean, following up from that technique, we could prove that the set of maps with metric entropy 0 is actually a dense G delta set in our space. And I want to speak in the rest of this presentation. I want to speak about the arguments, how we did that.
So we can remove now the
Yeah.
Okay.
Yeah. Right. Okay. So we want this. Generic F in C lambda has, measured theoretic entropy being 0.
But can you just explain the seminal paradox that if we now fix this generic set where the topological entropy is infinite, and we know we have the variational principle, so why there is no contradiction?
Yeah, so this is just the one measure, right? I mean, you look at the Lebesgue.
approximate by difference. Measure theoretic entropy for a sequence of
Right.
It's for the, okay, I got it. Okay, yes, okay, so.
Mm-hmm. Okay, so for that, we first proved one lemma, which says the following, and I will denote it by C lambda without I, because we're always an I. We have F from C lambda for every J, and I denote this J by A, B, an interval in I, and every epsilon greater than 0, there exists delta greater than 0, so that if G is in delta ball of in delta ball of F, then it follows that the measure of the symmetric difference between the preimage of J and the preimage of with F, preimage of J with F and preimage of G, right? And then preimage of G of J is smaller than epsilon. So for every interval J, we know that for every epsilon there exists delta, so that if we are in the supremum metric, of course, delta close to f, then the measure of this symmetric difference is smaller than epsilon. And let us prove this. So, okay, fix epsilon greater than 0, set delta to be between epsilon over 4 and greater than 0, and we define h delta to be the pre-image of this guy, not AB, but we shrink AB a little bit so that we add delta.
Recording in progress.
Okay. Should I start over? Or what does it mean?
No, but sometimes it says it for me. It doesn't mean anything.
Okay. Good. Right. So we have this H delta, the pre-image of this shrink interval, because the bigger interval J was AB. And what can we say? Then we have two things. The first one being, well, the Lebesgue measure of J is equal to the Lebesgue measure of the free image, by the definition. But this is greater than the Lebesgue measure of H delta, because J, this is contained in J, right? This guy is contained in J, so here we have, and delta is greater than 0. Okay? Right? So it's the measure of this guy is smaller than the measure of this guy. This. But now we want to evaluate it down. However, because G is in delta vicinity of F, it means that this is greater than lambda of, again, F minus 1 of J.
Excuse me, where is J?
J is an interval.
Yes, because you claim that A plus delta, comma B minus delta is in J. It's contained in J.
Right, yeah,
So
so
who is J?
AB.
AB,
Is written there.
AB. J is AB.
I couldn't read that, so it's for this.
Sorry.
Yeah, okay, this was my question.
Yeah.
Okay,
J is AB.
Okay.
J is AB. Okay, I saw that you were confused and I didn't know. I'm silly or something. Yeah. Right. Second. Yes, of course. But if we subtract epsilon over 2, this will still be smaller than this guy, and that's because, remember that component argument that I had, how to look at the Lebesgue measure preserving maps. If your slope is smaller than 1, then you cannot be Lebesgue measure preserving. And this actually says exactly the same thing. You have delta on each of the sides, so you can subtract 2 times epsilon over 4, right? So we have that we have this inequality, okay, let's denote it with 1, but not only this, if we replace this f with g, we will still have the same thing, right? Because we have this inequality for lambda of j. This is lambda of j as well. So we have lambda of j greater than lambda of h delta greater than lambda of j minus epsilon over 2. But this is also the same because we are Lebesgue measure preserving. This is also the same as lambda of the pre-image of j with g. This is without thinking, right? I just replaced it with g. Okay? Blah, blah, blah. 1, 2. Right? And so we can tell what's the symmetric difference. What's the measure of the symmetric difference? Well, let's look at this definition. So it's the j union, okay, minus 1, g minus 1, j minus the intersection. Okay? But we can write this, because this guy is contained here, we can write this as measure of the union minus the measure of the intersection. Okay? And furthermore, we can write this as the sum of the two measures minus the measure of the intersection, right? So it's, and because we have that the measure of the pre-image of j with both of these guys is the measure of j, we have 2 times measure of j, right? Minus 2 times measure of the intersection. Right? I didn't do anything extraordinary here. I just used the fact that it's Lebesgue measure preserving. Okay, but right, but h delta is contained in this intersection. F minus 1j intersect to g minus 1j. So this means that we can now use this inequality. So this is smaller than, so this guy is inside. So this means if we subtract this guy, we will subtract something less, so that the so that the outcome will be bigger, right? We are evaluating it up. So we can subtract this guy, but we can also subtract even this guy, right? So so the measure of this guy is more than the measure of this guy. So we can subtract 2 times the measure, so it's lambda of j, minus, we can subtract 2 times the measure of j, minus 2 times epsilon over 2, which is epsilon. But, yeah, so, and this finishes the proof. So here I used 1 plus 2. But this is then very helpful to use when estimating the entropy, right? So, okay, how much time do I actually have? I have something like 10 minutes. Okay, something like 10 minutes. So maybe I'll do this part a little bit quicker. So, right, okay. So now if we have partitions P1 to Pk, they are intervals partitioning I. Okay, I can do it this way. So I define this usual function h of p as minus I log lambda pi and over hn of f p is defined as 1 over n h of, and we use the join. I'm just writing down the definition of the metric entropy, right? Through the partitions, and then we will use it. N minus 1, the iterates of this partition P. Now, Hn is decreasing in n, so the limit exists, right? So we have that HFP is the limit when n goes to infinity of Hn of Fp, and then the usual definition of metric measured theoretic entropy is we take supremum of sorry? Yes, over P. So over all finite partitions. Okay, and one important part that we used here is the following. So if we have Pi being the partition assembled of the intervals to the I, j plus 1 to the I, where j goes between 0 and 2 to the I minus 1. So this partition is generating, right? So what I want to say is I can skip this part with the supremums. Actually, I can just look at the limits.
So it's you mean that the families are generating, not the, right? If you take now lim I goes to infinity.
Yeah. So h of f is the lim I goes to infinity. The families are generating.
It's a family.
Yeah.
Because you don't know of a specific partition which is generating.
Yes, you don't know.
Actually,
families are
it
generating.
seems, probably there isn't.
No, there isn't, because you can get more.
Yeah, the families are generating. But yeah, you can look at it then as a limit when I goes to infinity of the h f. And we use this at some point. Right. Okay. I had to write this down to get to the next proposition. And the next proposition says, okay, if we have a partition, again a finite partition, and f in C lambda, we have that the function which maps f to h n of f p is continuous. Right, and okay, if I want to finish in time, I won't go through the proof of this. However, this is using lemma, this lemma for all f minus i's and g minus i's. So this lemma is saying that the symmetric difference between these two guys is going to be small. But also we can apply it for the higher iterates of f and g. So choosing any partition element p, we know that f minus n of j is close to g minus n of j. And then if we have elements in the intersection that are given with these joins here for f, we know if we have, let's say, m elements, we know that if we chop just a little bit, if we have m elements that have non-empty, non-zero measure, then we chop just a little bit from every of that set, and we know that we have at least that many sets as f hat in G, right? So we have this correspondence. We have this number of guys that have non-zero measure here with f, and this at least that number of guys in G. And because of applying this lemma for all these f n's, we know that also the difference in the sums is going to be arbitrarily small. We just adjust this delta so that it fits, because we have finitely many conditions. That's the crucial part. We have finitely many conditions, and on these conditions we adjust delta being so small that that we have the two sums, one with f and the other one with g's, being very, very close together. But then there is a tail that remains for g. However, that tail, because we have both of them being measure preserving, is just this same fraction that we took out from all the f's. So, and because that small fraction was bounded, very small, also the tail is very small, which then proves that this map is continuous. So it's essentially using the lemma for fn iterates, so for the fn's. Right? Okay, so and now I want to get to the theorem. Now, proof of theorem. Okay, and now we define G beta being what? So it's the set of maps in C lambda so that Hn of Fpi is smaller than beta for some beta greater than 0. And I take intersections when k is greater or equal than 1 of the two unions, 1 going over all n's, so n greater or equal than k, 1 going all over the i's. And I claim two things. I claim two things. G beta is dense G delta in C lambda. And the second thing I claim is that G beta is actually the set of maps in C lambda for which the measured theoretic entropy is smaller than beta. So if we have this and this, let us just see that we actually get the theorem. How do we get the theorem? Well, I'll write it here. We take G to be the intersection of G1 over n's when n goes from 1 to infinity. These guys are all dense G delta in C lambda. So the intersection of them is again dense G delta set. And furthermore, they have arbitrarily small measured theoretic entropy. So this all the maps here have zero measured theoretic entropy. Okay, and I ran out of time. Okay. Right. So for this number 2, if I go, do you want to hear why this holds or not?
1 is more interesting.
No, 2 is
No, 2 is more interesting. Okay, then yeah, I can solve one.
to start with.
Yeah.
Otherwise you have
I can then show why G beta, why 1 holds. When 1 holds because proposition gives the openness.
G1 over n, you know that Hn, P, but it's the, no, but it's the I bigger than K. You know it's less than 1 over n. So you just use monotonicity to get, so it seems 2 is trivial. It's 1 which is not trivial.
Yeah, that's monotonicity. It is monotonicity, yeah. It's monotonicity of the two things, right?
You're all dense. That's crucial.
Yeah, that's
the center. So
right. I mean, you're right. There are two monotonicities: monotonicity in N and monotonicity in I.
But it's in the definition.
But it's in the definition, so it's actually.
So how do you see the density?
And okay, yeah. So we were a little bit. So openness follows from here.
But this is always
but the denseness was proven by Jozef and Serge in a different paper. What they've proven is that for every C in 0, 1, the piecewise affine maps with measured theoretic entropy equal to C that preserve measure lambda are dense. And this then implies what we have. So actually,
Continuity, right?
yes. So actually, what Serge and Jozef were asking for quite some time was. I'm done. Actually,
there is nobody, we don't have here
No.
another class.
But yeah, so the crucial step that they didn't notice is this, having this lemma, which is also not difficult to prove.
But can you give me a heuristic? Because now it was like it's a black box, right? You just say that there is another paper.
Yes, about that, they actually proved even more. They proved it for piecewise affine Markov maps. That the piecewise affine Markov maps are dense, and the procedure that they use there is delicate. Right. So
We know what is this G-deck.
sorry.
Yes, but we know what is the G-deck. We just have to prove that this was a fine map.
We want to prove it's known as the half.
Yes.
Then
Yes.
it's always that.
Yes.
If you
So,
prove it as non-empty, then
Yeah, of
I
course,
can
there's,
believe it.
yeah.
I can believe it.
right. Okay. Yeah. So, well, okay. Yeah, but this step is.
Some construction.
It's a construction. They use these. Okay. Okay. Yeah. I would also need to look in it a little bit more. But they use these window perturbations again. The window perturbations I was giving you the argument for the topological entropy, and sort of with those piecewise affine maps, the piecewise affine Markov maps. So for them, they know they can. It's like this. They can handle the measure theoretic entropy for them. They develop tools with which they can handle the measure theoretic entropy for the Markov case. And so that part is the most intricate part of the construction. But okay, but however, they were missing this also not that difficult lemma to get the whole proof, right? Because the openness depends on this lemma. And I just wanted to finish with a remark or two. Actually, metric entropy 0 means that the map is almost invertible almost everywhere. So this means that there exists an F invariant set, so that it has measure theoretic full measure.
Yes, which is
Right.
when you have the invertible.
Exactly, where you have the invertibility, which is then it is pretty surprising. On the other hand, these maps are nowhere differentiable, right? So what we also can say is we can say what the level sets are. Level sets are actually, except of the point 0 and 1, they all contain perfect sets. However, all the measure is contained on this invariant set, which is hard to me. For me, it's hard to comprehend. It's sort of okay. It's a wild map. It's a very wild map.
So for each level set, which is kind of large, you can pick up just one point which contains all kind of the measures.
So it's on a graph in some sense.
Yeah, it's on the graph. Yeah, right. Okay. Yeah, I wanted to finish with this particularity, and that's it. Thanks.
Okay, so are there any questions? I think there were many questions during the group, so
I like this.
I have a question.
please.
Yes, or maybe I'm not visible.
Okay, so my question is that how is you have defined some interval maps with with some crookedness. So how are these maps different from Hofbauer's piecewise linear maps?
I did not understand completely. How are they different from?
Hofbauer's piecewise linear maps. So Hofbauer has a lot of he has a lot of papers on some piecewise linear maps that he has defined. So the dynamics of crooked maps and the dynamics of piecewise linear maps, how much are they different?
Yes, so these crooked maps are not piecewise linear. However, they can be, of course, approximated with piecewise linear maps. Well, okay. So this is sort of a general question. Are you interested in some specific question related to this? I mean, these maps.
No, I mean when you are investigating the dynamics, right? Do you see any difference? Do you see, like, whatever you have studied? Do you see any difference between these and those? I mean, that's just because once you defined it, I just thought they would be topologically conjugate.
No, but they cannot be topologically conjugate. Okay, so these maps that I study, these generic maps, they are all they are not piecewise linear, right? They're not.
Yeah, they are not linear. In that sense, they're not linear in that. So they are not piecewise linear. But the dynamics I'm concerned of, the dynamics that they give.
The crooked maps.
I think
Yes.
What is the difference in the way you are studying?
What? So you were asking what's the difference in the way we are studying them?
Yeah.
Yeah. So okay, we are approximating them with piecewise linear maps.
Oh, so but then when you are approximating them, right? I mean, I'm looking into the dynamics, right?
Yes.
So dynamically, are they same? I mean, are they conjugate dynamically, or you find some difference between the dynamics there and here?
But so your question is just having the piecewise linear maps on the interval, preserving Lebesgue measure, and study them.
Yes, exactly.
First question is this a complete space? You know, if I would want to do a study like we are doing, then that's the first question, and I'm not sure it's.
But if you have bounded turning points.
If you have bounded turning points, then yes.
Then it's complete. And then
it's
is
complete.
This classical then? Everything is known?
I would need to look into that. I'm not completely sure, but yes, if you add some additional conditions, then the set that you're studying is complete, and there are nice questions like you asked. Yes, I'm not aware of.
Okay.
We need to check the literature with respect to that.
Okay.
Yeah, but that's a good question. Yes, that's a very good question.
So there's a lot of theory, I think, and this is like Vienna University. I think that is what was studied long back, right? Because Hofbauer was Hofbauer, Peter Oprocha, right? They were studying almost all properties of piecewise linear maps. So I just thought that this is like just a polished version of that, because then you're removing linearity and you're introducing crookedness.
Okay, yeah, you can look at it this way. Hofbauer. So this is Franz Hofbauer, right?
I see.
Yeah.
Well, yeah, I would need to look at. I mean, I wasn't thinking. I never was thinking in this direction that you were.
Okay.
No, but yeah, that's a good question.
Okay.
That's a nice question.
So thank you.
Okay. Okay. That's all. That's all. Okay. Thanks.
Thank you. Thank you for the question.
Okay.
I will look into it and.
Any other questions? Well, if not, let's thank Jernej again.
Thanks for setting it up.